3 squared. Going to beat me to it. Hurry, 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 hurry. Go for it. 200 squared minus 3 squared. I'll try and keep up with you. Google's going to help me. Okay, I'll get that one. And then if I take it to the half power, that'd be square rooting it, right? Somebody got it. I'm going to compare 199.25. Is that what you got? Does that seem reasonable? What's the deal with what I wrote in there? Does anyone have a problem with what I put in there? What does that 3 actually represent on the bottom? Oh, yeah, this is not. And be careful. It's actually, remember, there's a scale that goes with this. So just watch out. The only thing you have to watch out, it's not 3 on the bottom. It's actually 3. Remember, each of those is 20. The wind is 40, and that took 2 blocks. So it's 3 times 20. That's going to make that number look a lot better. But it didn't look like that's. Both those numbers just weren't kind of reconciling with what made sense. So you have to be careful. All these numbers actually represent something. If this is 200, and this is a lot shorter, 3 times 20, that's 60. That makes a lot more sense, the wind. Okay, so that's 60 on there. And then 206, so you can put 60 squared in here instead of. Okay, so let's put that in our calculator. Let's see what happens. Thank you. So 200 squared minus 60 squared. It is, does that sound better? 190.778. Now I was looking at squares over here. So the difference is, if you're counting squares, you just have to remember this is squares. If you want to know the actual speed of the plane that's going with it, these are 20 each. So we can use that. That's fine. It's just at a different scale. So this is 190.77, or 0.8 roughly. Okay, so I'm going to put it in my picture. So these are the things that we just got on my calculator. I have, let's see, 100, 200 here. This is 60 here. 200 squared minus 60 squared, 190.8. Now, that's just the length of that side. Now, if you want to find out how many squares it is, you divide by 20. I guessed 9.5. So you ready for 190 divided by, or 0.8 divided by 20? Come on, 9.5. How close am I? I was really close. So it really is about 9.5. Okay, so just wanted to make sure that I could find the exact amount. So in that picture, the actual speed of the plane is just, you can do 5 units over and 9.5 up. We're going to find the hypotenuse, but then we just have to remember to take it times 20, because each square represents 20 miles per hour. Okay, so 5 squared plus 9.5 squared. And then we'll square root it. And we'll get that distance up here, or that speed. I'm going to call it S instead. And I'll take it as, you want to beat me to it again? Be really nice. So 5.5 squared. That's 25, so 5 squared. This one's plus. And that is 9.5 squared. Square rooted. 9.53 again. 10.735. What do you think? And that would be times 20 to get the speed, because it's 20 units. And then you guys check me, because I don't want to write any. 214.71. So we just found this to be about 214.71 is the speed. Does that seem reasonable? If we were at 200, the wind comes along, blows a little bit behind us, so that means that we're going faster, and we definitely are off course, like it's going a different direction than what you would set your nose toward. It's faster because it's a little bit behind you. And so it's 214.71 miles per hour. This is my favorite part of vectors. Every number you write down, if you have just a little bit of sense of the context, will make sense. Like, things that are longer should have a larger amount. They represent like how fast you're going, the length of the vector, which way it points is the direction you're going. It's very mechanical. And it all, so when you write a number down, you'll know if it's right or wrong just because things make sense and you've used, and I want you to live in common sense when you're dealing with these. They're a lot of fun. So it's all right triangles. You're just solving right triangles. finding the lengths of sides, finding the length of a third side if you have two sides. So sometimes we'll use SOHCAHTOA in there as well. And this is the last piece. Speaking of SOHCAHTOA, what's the direction it's moving in this particular triangle? You're welcome to use either the sides that we have right now, the 5 and the 9.5, to get that angle. Okay, so this is my speed one. This is the, remember, this is my resultant vector, the green one that I was talking about before, when the wind is kicking in. So I'll highlight that in green for you. That's what I'm finding. We know this is 5 units over and 9.5 units up, roughly. That's not the actual miles per hour. We'd multiply by 20 if we needed to. But either way, we can find that angle, the direction that it's traveling at, and it's always from 0. So the wind direction is from 0 degrees. The wind is going 0, so everything is from 0. So the word direction is actually loaded. It's meaning something. Direction is from 0 degrees, and it's in the counterclockwise direction, kind of like the unit circle. To get that theta, I think usually the easiest one is tangent. So you all know that tangent of theta is the opposite over the hypotenuse, 9.5. Now this is where, remember we on the tomorrow's test you guys are solving trig functions, so you'll run into this. And this would be one where this would be approximate. It's not on the unit circle. So you'd grab your calculator and you go inverse tangent to both sides to cancel this out. So you'd solve. So tan -1 of this side and tan -1 of this side. Right? And you'd get theta is the inverse tangent of 9.5 over 5. Okay, and your calculator spits something out. You have to be cognizant of what direction is, because half the time the angle your calculator gives you is going to face the wrong direction, because your calculator will give you some answer and you're going to have to add 180 to it. And the only person who's going to figure that out is you, just saying, that doesn't make sense, I need to add 180 to it. So just use your good judgment and you'll be fine. I do need your help with this one because I can't easily do trig right now. So what would you get for inverse tangent of that? Somebody throw me an angle. You'll be right. Inverse tangent of 9.5 over 5 in degree mode.
52.24.
Yes, D. That's awesome. Thanks, Taylor.
62.
Dang it. Aiden, someday I'll let you be Aiden again. 62.24 degrees. Sound reasonable? And that's what you say every time you write something down in vectors. Does it look reasonable? Does it make sense in the context? The picture is absolutely essential. So now, the only thing I can do to this, I wanted to give you a little sense of the context of where vectors kick in and why they're very mechanical. They're right triangles. It's just solving right triangles left and right. The rest of this stuff that we start into tomorrow is ways of writing the vector. So it's all about describing the arrow. Sometimes we use the angle. We say, hey, it's a vector that faces this angle with this magnitude, kind of like vector from the movie. He has a direction and a magnitude. Sometimes we talk about it as what are the x and y components of that vector. Sometimes we use that language too. Two ways of describing the same thing. Do you want to tell me the angle and hypotenuse, or do you want to tell me the two legs? They both describe the same vector. And we like those forms for their different purposes. What we'll do sometimes is just draw a triangle and then solve for whatever we need. That's what all of this ends up being, is we solve triangles, we add vectors together, we solve right triangles to get to results. If you flip to the second page, there's this fancy little language in here. I'll show you guys engineering notation. But vectors that we talk about often come in these things called chevrons. So this is just a little preview of what's coming up. Chevrons are those little arrows. They were very popular about 5 years ago. Everything was chevrons. I think we're back to stripes right now, which is the current trend. But when you have I and J, engineers use that. It really means the same thing as the one next to it. It's a vector with horizontal and vertical components. These are like XY components of that triangle of the vector. And so tomorrow we'll talk about the notation and what you expect out of it. It's really easy to follow. It's just right triangles. They're kind of fun to look at. Chevrons, it's a new thing. Thank you a lot. That is enough to kick you into that assignment. And I think